Greetings. This is the second part of the lecture on torsional members, which will now focus on torsion of non-circular cross-sections. This video presentation is part of a series of lectures for the course CE235a Advanced Structural Analysis. And I'm your instructor, Arturo Tachiroglu, professor at UCLA. So let us begin by reviewing the kinematic hypothesis for circular members. And in the circular members, we remember that the plane sections remained plane. This was the Coulomb hypothesis, which was equivalent to the Bernoulli-Euler hypothesis for transverse bending. The cross-section remained planar, and there was no warpage. For this hypothesis to be valid, we stress the fact that the cross-sectional geometry was either a solid circle or a tube. Just let's recap that discussion here. If we have a circular cross-section, if we painted a rectangular perpendicular grid line on its surface, if we apply torque to it, we see that the vertical lines that sort of represented the cross-section remained vertical. They did not become wavy lines or got warped, and the horizontal lines twisted around the circular geometry. And the only thing that appeared to be changing was the angle at the grid lines, which were 90 degrees, but now they could be different. So here's a photograph from an actual experiment. If we painted a white patch on the side of a circular shaft and applied torque to it, we see that the vertical edges remain vertical and straight, and the horizontal edges simply rotated, giving rise to a shearing angle or a twisting angle. If we look at solid non-circular shafts, we see that in real life there is warpage, and the Coulomb hypothesis no longer holds. So here's the similar experiment that you would carry out on a rectangular shaft. Again, you have the perfectly perpendicular grid lines, and if you apply torque to this shaft, the vertical lines will become wavy, they get warped, and the horizontal lines also rotate and do other things. But this is a more complicated problem than the Coulomb problem, and it will require a more sophisticated solution approach in general. Here are photographs from a physical test. If you take the same sort of illustrated circular rectangular shaft or shaft with a square cross section and paint a white square patch on the side of it and apply torque, you see that the edges get warped. These deformations, these warpages can no longer be ignored. They actually contribute significantly to the solution. Another critical aspect of the behavior of the solid non-circular shafts compared to the circular ones is the distribution of the shear stresses within the cross-section. So if we're looking at non-circular shafts, we are definitely looking at shafts whose cross-sections have edges. So what happens to the shear stresses at those edges besides the warping of the cross-section? So it turns out that in the circular shaft, if you recall, the cross-sectional shear stresses were 0 at the centroid, and they became a maximum at the perimeter points. But at the corners of a non-circular shaft, at those edges, the shear stresses must be 0 due to balance of angular momentum. This is quite unlike the distribution we encountered for the circular shaft. If we take a closer look at a material element at that corner, take an infinitesimally small cube, we will first observe that the lateral sides of that cube are traction-free. Therefore, the shear stresses there are 0, and from the balance of angular momentum, both components of the in-plane shear stresses must also be 0. So this is quite different than what we had seen or shown for circular shafts. So the solutions to the torsion of non-circular shafts is a more involved process, and I'm not going to give you the details of such solutions, but know that such solutions can be found in standard elasticity books, and such as Timoshenko. So I refer you to them, and you'll see there that there are different classes of solution techniques based on stress functions as well as bubble analogies, etc. What I will do in the limited time I have allocated for this little presentation here is to show you some example solutions so that you can interrogate their character rather than showing them how you derive them. I will show you what you obtain for different sections. I consider 3 cross sections for this purpose: equilateral, triangle, square, and ellipse. And of course, ellipse is a more general case for the circle, so whatever solution I put up here should be a sort of a superset of the solution that we had obtained for the circle early on. I will give you the maximum shear stresses for each of the 3 cases, which will occur at the midpoints of the edges marked by these white circles. And for example, for the equilateral triangle, the tau max is going to be 20 times the torque divided by a cubed, a being the side of the length of the equilateral triangle's side. And the other solutions have different coefficients determining this tau max. Also, in a cantilever situation, if you apply the tip torque, you can compute the tip twist for all of these cross sections. And for example, the tip twist for the triangular section will be 46 times the tip torque times the length of the shaft divided by a fourth times the shear modulus. And if you explore this subject a little bit deeper, you can actually prove that the most efficient cross-sectional shape against torsion is a circle. And perhaps not surprisingly, you see many shafts being used in practice today to have circular shapes. They're either solid circles because they're multifunctional and they might be under other types of stresses besides torque, or thin-walled members like tubes. Let us examine the response of a triangular shaft and explore a mock design problem. Let's assume our design criteria is twofold: that we have an allowable shear stress of 8 ksi and an allowable tip twist of 0.02 radians. So what is the maximum amount of torque that we can apply, say, to this shaft with a equilateral triangular cross-section of 4 feet length? We can check for allowable twist, and our formula, if you recall from the previous slide, was for the triangular section was allowable twist was equal to 46 TL over a fourth times G. So we set the left-hand side to be 0.02 radians, and all the quantities on the right-hand side are known except the torque, so that from this we can compute the torque that will create that much tip twist, and that becomes that happens to be 170 pound-inches. We can also check for allowable stress using the formula we've seen in the previous slide. Set the allowable stress on the left-hand side to 8 pounds per square inches, PSI, making sure that all the units are consistent on both sides. And the only unknown, therefore, on the right-hand side will be the torque, which we can compute to be 1,350 pound-inches. Between these 2 alternatives, the smaller one will obviously govern the design, because at that torque we will have reached the allowable tip twist criteria, and we would have reached it first before reaching the allowable shear stress. Let us now assume that we have the same amount of material and we want to make a circular shaft out of it, and then we want to find out that circular shaft, what that circular shaft can take as torque, given the same exact design criteria that we have applied to the triangular one. So if we're keeping the lengths constant, then the area of the circle or circular cross-section must be equal to the area of that triangle. From this we can compute the radius of the circle, equivalent circle, and that's 0.557 inches. And then we can go to the allowable twist criterion for circular shaft, and our formula there was TL over GJ, and we set the allowable twist to 0.02 radians and compute the necessary torque to reach that twist. That becomes 233 pound-inches. We can then check the allowable stress criterion, and that's our torsion formula. So we plugged in C for the radius and set the allowable shear stress on the left-hand side to be 8,000 pounds per square inches. The only unknown again there is torque. We compute its value to be 2,170 pound-inches. Again, the allowable twist criterion governs, and this torque that the circular shaft carries now is larger than what the triangular shaft could carry. In fact, it is 37 more percent torque that you can apply to the circular shaft of equal volume material. I have not derived the governing equations and the solution of those equations for torsion of non-circular shafts because it's a little bit more involved than the circular shafts, but I can and will derive you the governing equations and various useful relationships for thin-walled tubes with closed cross sections. So consider a thin-walled shaft, and it has a thickness of t, and this t can be a variable t that it can change around the circumference of the shaft. And we apply a torque in the direction of the x axial coordinate. Let's assume that we take a slice out of this shaft and just put a picture of that slice up close so that we can see it. The thickness of this little segment of length s around the circumferential direction is TA at point A and TB at point B, and it has a length along the axial direction of dx, so it's infinitesimally long along the x direction. In this free body diagram, we have exposed various shear stresses, and those shear stresses that we have exposed within the cross section are tau A and tau B at points A and B. And of course, from balance of angular momentum, the shear stress along the x direction at point A must be of the same magnitude as the in-plane shear stress tau A. And if the tau A is running to the corner, then the tau A along the x must also be running towards the corner. At point B, tau B was running away from the corner, so the shear stress along the x direction must also be running away from the corner and has to have the same magnitude. Now we can go to those two sides and compute the resultant infinitesimal, of course, force at those two places. I'm calling it infinitesimal dFA and dFB because they're acting along an infinitesimal length dx. And those resultants are easy to determine. First and foremost, they are equal to each other from the balance of balance of forces along the x direction, and then there are no other force resultants acting on the surfaces of this little object because this is a pure torque problem. So dFA is equal to dFB, and their magnitudes are simply computed by tau A times TA dx and tau B times TB dx respectively. And if we collect the two terms together, we see that the dx's will cancel, and that tau A times TA is equal to tau B times TB. So this is an important thing to observe, that while tau itself may be different at different positions along the perimeter of the section, and tau TA may also be different, their product appears to be, or is proven to be rather, constant. Because I did not choose the separation between points A and B to be an infinitesimal separation, and it was an arbitrary length s. This means that everywhere along the perimeter of the cross section we have this product to be constant. Let us now take a look at the front and back sides, and to do that I'm going to now cut up the object into a small infinitesimal size along the s direction as well. And in the front side I'm going to have df, and in the back side I'm also going to have df, and they must be equal to each other. I don't have to rename them separately to show them that they must be equal, because it's obvious since there are no other forces acting along the surface, inner and outer surfaces of this shaft. These two forcelets must also be equal to each other. And then if the shear stress, the average shear stress acting on the front patch is labeled as tau average, then the one in the back must be of the same value as well. So the area that we have shaded here, where along which the tau average is acting, is dA, and that is simply T times ds. And therefore the dF that we have just talked about must be equal to this tau average times the little area dA, which is T times ds. So if tau average times T is a constant, this means that dF over ds must be constant. And this term is called, this constant quantity, which is the product of shear stress and the thickness there, is called the shear flow. So shear flow across the cross-section is constant. If the thickness increases, the shear stress must decrease in return to keep the Q constant as it is. So again, dF is equal to Q times ds, and or shear flow Q is equal to dF ds. So whatever this force is around the circumference, its variation with respect to the s coordinate is a constant. It is not zero, but it is a constant. Then the other trivial third direction that we need to consider is the vertical direction, and we see that because the top and bottom surfaces of this little object are traction-free, stress-free boundaries on the top and the bottom, this implies from balance of angular momentum that the vertical component of the in-plane shear stress, the radial rather component, must be equal to zero in the front and the back sides. So that's a trivial observation. Now that we have understood something crucial about the shear stress distribution within the cross-section, we are now ready to relate the shear stress distribution to the torque that created it. So for that, I'm going to now make use of this dF that I have computed before in terms of the average shear stress at where it's located. dF, if you recall, was simply tau average times dA, and that was tau average times T times ds, and tau average times T was the constant that we talked about, the shear flow. So to compute the contribution of this little forcelet dF to the torque, I need to multiply its magnitude with its moment arm, which is denoted here as h. So dt will be h times df, and I can substitute the formula that I've obtained for df to obtain h times t average times t, tau average times t ds is equal to the d torque. If I integrate this quantity around the circumference of the object of our shaft, then this will give me the total torque. There, this looks like a formidable integral to carry out, this line integral or circumference integral. But let's make the observation that no matter where we go around the circumference, while tau average itself might be variable and also t, their product is always a constant. So we can take the product as a constant outside the integrand, and then we'll be only left with the job of having to integrate h over the circumference. And then I'm going to make a small observation going back to that small and simple observation going back to that blue triangle that we talked about. So what is the area of that little blue triangle? Well, that is a triangle. Its base is, has a length of ds and its height is h. So half times h ds will give us that little blue area, and I denote here as dam. So what we're doing here is we're integrating, when we're integrating HDS, we're actually integrating 2 times DAM. So if I pull that 2 out of the integrand, I'll be left with this task of integrating DAM over the entire cross section. This then gives me the median area as a result. So then once I've observed that, this now completes the formula for me. I now know how torque is related to the shear stress at any given location, and I can find the average shear stress using this formula by simply dividing the torque with 2 times the median area of the circular of the cross section, not circular, and the thickness there at that location. And of course, shear flow will be just this quantity multiplied by t, and that's just a constant. So recapping again what we have defined, tau average is the average shear stress acting over the thickness of the tube. T is the thickness of the tube where the average shear stress is to be determined, and AM is the mean area enclosed within the boundary of the center line of the tube's thickness. So now we have obtained the relationship between torque and the shear stresses at any given location. Now we need to consider the deformations. So the deformation quantity, the metric for that in the case of torsion is twist. So how do we compute and relate the angle of twist to the applied torque for these types of cross sections? That is a question we're going to seek the answers for. Now we're going to utilize the energy argument for that, and remember that the strain energy density for this particular stress state, which is a pure shear stress state, was given by the following formula: du dv, shear stress per, the strain energy per unit volume is equal to half of tau squared over g. This was the case because this is the only stress component acting on any given cube of this object. And of course, then we can multiply both sides of this equation by dv, and then integrate it over the entire volume of the shaft. And we can split that volume integral into two parts, an integral along the length and an integral across the cross section. If we're looking at a prismatic beam where nothing is changing along the length of the member, not the cross-sectional shape nor the materials, then we can pull the g outside the two integrals, and also the outer integral will then be just L, giving us the result L over 2g times the integral of tau squared over the cross-section. That's the entire energy density stored in the system. And of course now we can use the torsion formula for this thin-walled members that we have derived just recently into this integrand, and replace tau with T over 2TAM, and observe that T is a quantity that does not depend on ds, neither 2, neither AM, those are all constants. We'll pull them all out. The only quantity therefore that will remain inside the integrand is T over T squared, which is 1 over T. So all we need to do to evaluate the strain energy, total strain energy, is to integrate 1 over T across the circumference and multiply it with that other ratio, T squared times L over 8G AM squared. And we know that if we differentiate this energy, total energy with respect to the torque, the result must be equal to the twist angle. And that integral is quite simple to carry out, and the result is TL over 4GA squared times the integral of 1 over T across the circumference. So sometimes for some problems it will be possible to carry out this integral in closed form, and for some problems it won't be, but for those problems you can resort to numerical integration to carry out that line integral of 1 over T around the circumference. So let us see if the thin-walled member approximation that we have obtained for these arbitrary sections actually reproduce the formulas that we have derived for the circular tube. So what I want to do is I want to compare the results from these formulas for a circular tube with those that we have obtained from the Coulomb solution. So if you recall, in the slide that we just saw, the thin-walled member approximation told us that the average shear stress was equal to this formula. And if we are looking at a circular cross-section that has a mean, that has a radius of Rm and a constant thickness of T, the Am is going to be equal to pi Rm squared, and therefore the tau average will be T over 2 pi Tr squared. We can then compare this result with that we have obtained from the Coulomb approach. So remember that the circular tube formula was that tau average was exactly equal to T times Rm over J, and then we have created an approximation, thin member approximation for J, and computed that J is approximately equal to 2 pi R cubed times T. If we make the substitution there and make the necessary simplifications, we see that the two results, the thin-walled member approximation as well as the circular tube approximation, give us the same tau average. That said, the tau average is all that the thin-walled member approximation gives us, whereas the circular tube approximation obviously gives us a tau max and a tau min that occur at the outer surface and at the inner surface respectively. And the average of those two values is indeed equal to what we've obtained from the thin-walled approximation. So the circular tube formula is a little bit more general still, because it gives us a trapezoidal distribution of shear stresses through the thickness, but then the results in many respects are identical to each other. Of course, the angle of twist that we have obtained for the thin-walled member approximation is simply this, and in this case the T is a constant, so we can pull the T outside the integral, and therefore all we have to do is just integrate ds over the circumference, which just happens to be 2 pi Rm. So that then gives us the tip twisting angle for the thin-walled member approximation. And you can compare this result with that you've obtained from the circular tube to confirm that they are indeed identical to each other. Let us carry out another example that involves a triangular tube. So here we are looking at an equilateral triangle, edges that have lengths of 200 millimeters. The total length of the shaft is 3 meters. We apply a torque at both ends, so it's in static equilibrium. We need to, let's assume that this is made out of A36 steel. The shear modulus is, for that material, 75 times 10 to the 9 Newton per meter squared pascals. We need to compute the median area, which is simple to do. It is simply 200 millimeters times sine of 60 degrees. That's the height of the triangle times a half. That gives us an area of 17.32 times 10 to the minus 3 square meters. Let's assume now we have design criteria of allowable shear stress 90 megapascals and allowable tip twist of 2 times 10 to the minus 3 radians. We can first check allowable twist to see what torque causes us to reach that allowable twist. So the formula we have to evaluate is this. On the left-hand side, the tip twist, the allowable twist is set to 0.02 radians. And on the right-hand side, we need to evaluate 1 over t times ds. And lucky for us, for this cross-section, the thickness is constant, so it just can be pulled out of the integral. So all we have to do is just carry out the little algebra in front of the integral, and the integral itself is merely the circumference of the triangle, which is 3 times 200 millimeters or 0.2 meters. From this, we can compute the torque to be 500 Newton meters. So if we apply this much torque, then the relative twist between the two faces of this shaft will be 0.002 radians. Let's check the allowable stress and use the formula we have derived before. The average shear stress here is T over torque over 2 times the thickness times the median area. We set the left-hand side of this equation to be the allowable shear stress, 90 megapascals. On the right-hand side, everything is known except the torque itself. And because the thickness is constant everywhere, this is the same exact shear stress that the triangular hollow shaft will experience anywhere. From this, we compute the torque to be 15.6 kilonewton meters. Of course, between the two, the smallest one is 500 Newton meters, and now that torque will govern the design. So this concludes our discussion on the torsion of circular as well as non-circular shafts, with some detail given on the derivation of thin-walled members under applied torque.